like to start by saying muchas gracias to the organizers. It's a very interesting conference, and I'm sure it was not easy to organize it given the current circumstances, so I appreciate it. What I will discuss today is joint work with Gleb Smirnov at ETH in Switzerland, and I want to start with an explanation of the title of the talk. That will be the first part of these 25 minutes. And at the end, I will hopefully be able to state our main results. So the object of study that I want to talk to you about today is certain cobordisms where two geometric structures in this Venn diagram, the one in black will be a spin structure, and the one in red will be a Lorentzian metric with a very particular property, coexist. So the talk is about this intersection of these two sets, so that I start motivating the structures. I'm gonna use cobordisms. As you can see from the drawing, I will denote with capital M a compact manifold with non-empty boundary given by, in this case, N1 and N2, which themselves are codimension ones of manifolds that are closed. And by closed, I mean that they are compact themselves, but they don't have boundary. Now, we're not interested in cobordism per se, but on structures on cobordisms. So I'm going to use this slide to motivate an example, the notion of oriented cobordism. So this will be a triple, as in equation 0.1, where you have an n+1 manifold whose boundary are these two manifolds. But the oriented cobordism, the structure is that now this N1 and N2, in this case I underline N2, is an oriented manifold whose orientation is induced by the orientation of M. Now this generates an equivalence relation that splits the set of manifolds into equivalence classes that, when taken with the disjoint union of manifolds, forms an abelian group. And what I wrote down in example in equation 0.3 is that this coding of information that I'm underlining in blue, it will be that the first oriented cobordism group is trivial. And what that means is that the circle bounds a two-disk. On the right-hand side, this means that the triviality of this group is just that any closed-oriented surface bounds a three-manifold. And stated for three manifolds is this theorem, which says that any closed-oriented three-manifold, you can always find an oriented four-manifold that bounds in such a way that the orientation is induced. The central object of study today are Lorentzian cobordisms. But before I go into the definition, I should state that these objects have been studied by many people, and due to time constraints, I am not able to mention most of them. In the paper with Smirnov, we paid particular effort to being careful with the bibliography, but there's a lot of names that I'm not gonna mention, like, well, today's paper, today's results are motivated by a result of Gibbons and Hawking, but there's work of Chamblin, Penrose, and several others. So a Lorentzian cobordism is gonna be a cobordism itself, so that's our initial data. And we want to equip this cobordism with a non-singular Lorentzian metric on the compact M+1 manifold that has a time-like vector field, so it's going to be a time-orientable spacetime. But we want for this Lorentzian metric to induce Riemannian metrics on the boundary manifold, so that when restricted to the boundary, this gives a positive definite inner product. Just to set up some notation, as I promised, I'm trying to explain the title, is that when we have a time-orientable spacetime, this might be redundant. I just want to be crystal clear that I'm considering time-orientable Lorentzian manifolds. The frame bundle is a principal SO1N fiber bundle, where this indefinite special orthogonal group, we're taking the identity component. Moreover, there's a result of Gerog that tells us that all these spacetimes will contain closed time-like curves, so they will violate causality. If time permits, at the end I will say something about some related Lorentzian cobordisms that do not contain such curves. Now, there's a related notion that, again, the cobordism is the initial data. There's a non-vanishing vector field, so non-singular, no zeros on your manifold. If you recalled, in the case of closed manifolds, a sufficient and necessary condition for the existence of a Lorentzian metric is the existence of such a non-vanishing vector field. Now, in the case of compact manifolds, meaning that the boundary is now non-empty, we want for this vector field to behave, have this transversal behavior on the boundary. In the drawing that you're looking at your screen, this V is drawn in red, and we want it to be interior normal in one boundary component and exterior normal on the other boundary component. So it's crucial that it hits the boundary transversally. Now, when we're looking for a Lorentzian cobordism, it turns out that it suffices to look for this normal vector field cobordism. This is not surprise because of the result that I just invoked, that the existence of an over-vanishing vector field gives you the Lorentzian metric. But I want to emphasize where the transversality at the boundary comes in. So this is the purpose of this slide, which I'm aware that it's very well known for most of you. So we have the usual definition of a Lorentzian metric on the compact manifold M, where G lower index R, is just a Riemannian metric. Now, under this definition, we have that once you assume that this vector field is transverse to the boundary of the submanifold, you obtain this basis, where again the EIs are just you're borrowing the part of the basis of the tangent space of n and a point n and the additional transversal vector field. And this yields a basis for this tangent space of M. Now you can decompose your Lorentzian metric given in 0.9 into components under this choice of basis, and this identity to some linear algebra implies that this pullback metric is, well, this pullback will be positive definite. So again, just to emphasize that this is the key point of what we want our Lorentzian cobordisms to have, meaning that you have a vector field that hits the boundary transversally. So we have that, again, we're searching for Lorentzian cobordisms because of what we discussed in the previous two slides. It's equivalent to look for a normal vector field cobordism. And it turns out, oh yes, sorry, I skipped this. Again, you have the Poincaré-Hopf theorem that when this vector field is transversal to the boundary, then you can determine its index in terms of the Euler characteristic of your manifold. This is, it is the case that you can have compact manifold with non-empty boundary, that do have nowhere vanishing vector fields. Now, the answer to the previous question, as the remark indicates, will come from the Euler characteristic of your manifold. And here I want to discuss a result of Reinhardt back from '63, also proven by Sorkin, is that, again, at the risk of repeating myself, the existence of a cobordism is the initial data. And they state that the only obstruction for the existence of this vector field, such that you have a normal vector field cobordism, is that the Euler characteristic of the n+1 manifold should vanish, provided that the dimension of the manifold is even, or that the Euler characteristic of the boundary components have to be equal if the manifold is odd dimensional. Reinhardt also studied, again, the algebraic structure of these objects. He showed that they form the equivalence classes under the disjoint union operation form an abelian group, and then you can take multiplication of manifolds and obtain a graded ring. And he also computed these two objects, 0.13 and 0.14. So the algebraic, the properties of a Lorentzian cobordism of a manifold can be algebraically encoded. All right, so going back to the initial Venn diagram, I want to now be a little bit more precise about what this overlap region is. Looks like a pie. As a definition, this could be given more rigorously, but for today I think it's okay. A Lorentzian cobordism will be a cobordism whose orientable frame bundle has this indefinite group as its tangent group. Now what that means, as the lemma indicates, is that you're going to have a space-time, so whose Lorentzian manifold whose orientable frame bundle has SO1n as a structure group, and that the tangent bundle of your manifold admits a spin structure. This is what the lemma is telling you. So this spin 1n Lorentzian cobordism will be a cobordism equipped with a spin structure. In this slide, I also record that spin structures on manifolds have been very well studied. They are very useful objects. Among the many things that among the many beauties they come equipped with is that they enable the usage of the Dirac operator, just to give an example. And there's this result of Milnor, that in dimensions 3, 5, 6, and 7, you computed that any spin and manifold bounds, so that the spin cobordism group is trivial. Okay, so now the question that kept us busy, Smirnov and myself, is under which conditions do you have a normal vector field cobordism such that the cobordism piece is a spin cobordism? And it turns out that these two structures need not coexist. I'll be more precise about this sentence in a bit. But the answer of when they do coexist is basically given by relating topological invariants that arise from the spin structure of the spin cobordism and those imposed by the existence of a Lorentzian cobordism. I'm using this notation jumping ahead of myself because, as I said, this is studied first by Gibbons and Hawking in the case of four-dimensional spacetimes with three-dimensional space-like boundaries. Now, we will need the following topological invariant to answer this question, known as the Kerber semi-characteristic. Now, as you know, for closed odd-dimensional manifolds, I apologize, for odd-dimensional manifolds, the Euler characteristic vanishes. So there's this modification that it's one of these switch-on, switch-off invariants, meaning that it's only mod 2, that takes the sum of the homology groups with the coefficient field f and when these conditions. So it only goes from 1 to k, where the dimension of the manifold will be 2k plus 1. And now as an example, so S3 is a 2 plus 1 manifold, so you only have that the contribution to the Kerber semi-characteristic is just that it's a connected manifold equals to 1, and when you take the product of S1 times S2, then the contribution is from the first homology group and the zeroth homology group. And since this is, again, an 0 or 0 or 1 is dichotomy of values invariants, this will be equal to 0. Now, this slide contains the work of Gibbons Hawking, which motivating the writing of this paper. Studying these things have been a lovely opportunity to study the work of a lot of outstanding people. And Gibbons and Hawking are certainly one of them. And this is a very enjoyable paper to read. So the starting point is 2 and 1 and 2 close-oriented 3 manifolds I didn't say that, but in dimension 3, as long as your manifold is oriented, it immediately admits a spin structure. And it turns out that they showed that there is such spin 1,3 Lorentzian cobordism if and only if the Kerber semi characteristic of the three manifold boundaries are the same. So in this case, they're relating the other characteristic of the manifold given by Reinhardt's theorem to the semi-Euler characteristic of the boundary three manifolds. Now, this example points out that, again, these two structures, the spin structures and the SO1N Lorentzian cobordism structures, need not coexist. So in the first line, there's this, if you take the handle body S1 times D3, so the boundary of that handle body that now you're watching in blue in your screen will be S1 times S2. Now, done carefully, you can remove 4-ball, small, arbitrarily small 4-ball away from the boundary, and these will yield a manifold, a spin manifold, whose boundary components are S3 and S1 times S2. So this line proves that this is a spin cobordism. Now, there's also an SO13 cobordism by, here I denoted M prime. Notice that to show that this Lorentzian metric holds, such that these S3 and S1 times S2 boundary components are space-like, it needs for M prime to have Euler characteristic equal to 0. So to do that, you just compute the Euler characteristic of this guy, and then you connect some with a 4 manifold. I believe RP4 does the job. So now you don't have the initial cobordism that you started with, meaning you don't have the initial M. You do have other cobordism, and that's the one that yields the SO13 cobordism. But it turns out that in this case, if you cannot have both your cake and eat it, sort of. In this case, you have a Lorentzian cobordism and you have a spin cobordism, but they won't coexist in the way that we described. And this is what it's claimed in equation 0.17. So this example shows that this overlap of the structures that I drew on the Venn diagram is not as straightforward. Now, our contribution is, I hope it's not so confusing, but like I said, this is based on work of a lot of outstanding topologists and people from Lorentzian geometry. So our contribution is the following statement. So again, the initial data is a spin cobordism that, notice the notation now, it's M hat, the compact N plus 1 manifold. Now, if the dimension is not equal to 0 modulo 8, then the existence of a spin 1N Lorentzian cobordism is equivalent to their Euler characteristics being equal in even dimensions. This is Reinhardt's result, simply. And in odd dimensions, provided the dimension is 1, 3, or 5 modulo 8, you require that the Kerber semi-characteristic of their boundaries coincide. In this way, we're extending Gibbons-Hawking result to higher dimensions. And then if the dimension is 7 modulo 8, then there's no restriction at all. Every such spin manifolds admit a spin 1N Lorentzian cobordism. So let me say a couple of words about the proof. The proof is basically algebraic topology. There's what we did is a minor extension of work of Kerber-Milnor, Lustig-Milnor-Peterson, Geiges. All these authors were looking at a similar lemma as the one sitting in your screen for other purposes, and we just generalize it to arbitrary dimension. And the importance of this lemma is that it relates the existence of in the presence of a spin structure, the existence of the Euler characteristic of the n+1 manifold cobordism and the Kerber semi-characteristic of the boundary. So whenever you have a spin structure, then this sum will be an even number. And that's the key ingredient. Gibbons-Hawking used the case of the lemma proven by Caveira-Milnor, and again we just extended to any even dimension. The proof, I'm not going to say much. I'll gladly ask questions about it, but just to point out that it comes from a cup product. Again, we're using some algebraic topology. We took the bilinear pairing, we're doing equation 0.19. Look at the congruency of the sum of the Euler characteristic and the Kerber semi-characteristic that holds in general, and then we use some characteristic classes known as the Wu classes and the spin structure to show that this sum is indeed even. The second key ingredient, and I hope I emphasize why in dimensions equal to 7 mod 8 there's no obstruction at all, is okay, so let's say that you start with spin cobordism. You can modify your n+1 manifold by doing surgeries away from the boundary and obtain a space-time such that the boundary remains unaffected, given that the surgeries are local operations. So, like I said, we're done away from n1 and n2. And you can perform these surgeries such that first you want M to also have a spin structure and modify the Euler characteristic of M hat, lowering so that it vanishes, and then invoke Reinhardt's theorem. Now, in the case of n equals 7 as an example, the case n equals 7 modulo 8, so assume again that you have a cobordism M hat. Now, out of it, we can build a new cobordism by taking connected sums with the quaternionic projective space and the torus of the corresponding dimension, 8q plus 8, such that this, depending on the values of the integers k1 and k2, you obtain spin manifold who has vanishing Euler characteristic. This is possible because in these dimensions, the Euler characteristic of the quaternionic projective spaces has these values. This is a statement that this manifold has a spin structure, so does the torus. The torus is parallelizable, so the connected sum will have zero Euler characteristic. So again, out of somebody gives you a spin cobordism, then you can modify that cobordism to get a spin cobordism such that the Euler characteristic satisfies Reinhardt's theorem. We also took care of the algebraic structure of these objects, much like Reinhardt's theorem and what is done in the case of oriented cobordism, complex cobordism, etc., etc. It shows that these sets form abelian groups and that you have the structure of a graded ring. And here we went a little bit further than Gibbons and Hawking and showed that, for example, the result can be phrased as there's an isomorphism of this group on your left to the group of index 2, set 2. And that isomorphism is, again, just the Kerber semi-characteristic. Now let me finish the talk by mentioning a couple of corollaries. In the case where you take dimension 4 has the boundary, then it turns out that you have a spin Lorentzian cobordism if the four manifolds are stably parallelizable and their Euler characteristics match. So the existence of this cobordism do place a lot of constraints on the manifolds. The four manifolds will have, well, they're going to bounce, so their first Pontryagin class goes out the window. The first and second Diffie-Whitney classes are also zero because you want a spin structure on them. And then the only thing that keeps them from being parallelizable is just the other characteristic. We have a group isomorphism into the free abelian rank 2 group, and we show that this is generated by the force sphere and the K3 surface. The similar results hold in dimensions 5 and 6, as you can see. They're the spheres of the corresponding dimension and are the n-dimensional spheres. The last line, now shaded in blue, is just the statement that in these dimensions, as I mentioned, dimension 7, mod 8, there's no obstruction, so that cobordism group is going to be the trivial group. And that's it for me. I want to thank again the organizers and thank everybody for their attention.